Yeah, so Dan just talked a lot about what you might use CASPER hardware for, building spectrometers, correlators, beamformers, all those good things. So I've got a more sort of hardware-focused presentation, which really leads you through the very specific bits of hardware we have going on next door in the tutorials that you'll be playing with at the latter part of this week. So firstly, what is the point of hardware? What do CASPER offer in the domains of sort of digitization, processing, and signal transport? Do I need this? I don't know.
I need because of the recording. Thanks.
I was hoping to escape that. Okay, so firstly, what is the point of hardware? I've never really felt there needs to be a point of hardware. I just like playing with toys, but you know, it turns out to get money from the NSF, you have to claim you're doing some science. And largely, hardware that we use in CASPER performs one of three jobs: either digitizing signals, we are after all digital signal processing collaboration, processing those signals, or doing some sort of data transport, sending, receiving, shuttling huge amounts of data around the place. And CASPER sort of has hardware in all of these domains, and the idea is you sort of look at your particular requirements for a project, pick the best piece of hardware that suits your specs, and get to work, you know, putting together a system piece by piece. And as Dan said, the idea is it's all nice and modular, it's all nice and scalable, so the work of your predecessors can go on to making your instrument easy to build. So step one in digital signal processing, always to digitize. I'm just going to skip over the fact that there might be a really complicated RF front end. RF engineering, as we know, is witchcraft and magic. We shouldn't worry too much about it. Things really get interesting once you have digital number streams. So when we're talking about digitizing signals, obviously the bit of equipment we need is an analog to digital converter, an ADC. What's an ADC's job? Well, it takes analog inputs in, usually on some variety of coaxial cable, and it outputs digital data. And, you know, it might output digital data in any one of a number of different forms, but ultimately bits on a wire connecting to some downstream digital processor. So ADCs are relatively easy to characterize. I should say in this talk, I'm really going to gloss over all of the details of everything, because I'm fast and loose, that's how I roll. So, you know, obviously when characterizing ADCs, there are, you know, very, very subtle effects and measurements you might want to do to make sure you have an ADC that performs exactly the way you want. But at the very highest level, the things you're looking at when picking an ADC are A, speed. How many samples per second do you get out of your ADC? So as Deepti and some others have talked about, the faster you sample your analog streams, the more bandwidth you can capture and process in your digital system. You know, the Nyquist criterion states, you know, that the amount of bandwidth you can process unambiguously without aliasing is half the sample rate. So faster samplers mean wider bandwidths you can process. How many bits do you get out of your ADC? That is, if I'm sampling a voltage, are the digital numbers that are going to come out of my ADC, do they run between 0 and 255, in which case you're talking about an 8-bit sampler? Do you need a larger dynamic range? What's the sort of relationship between the biggest signal you need to represent and the smallest signal you need to represent? That's going to determine how many bits you need. Oftentimes in real life, that reflects back on what's the sort of environment you're operating your system in. If you expect lots of RFI, maybe you're measuring a very, very small signal, but in the presence of large, bursty interference signals, maybe you want to be able to represent a very large range of voltages. Once you've got a speed and a number of bits, now how many channels do you want? How many different independent analog streams do you want to digitize? So in the simplest case, maybe it's just one, maybe it's two, maybe you have a dish with a single receiver, but it's dual polarization. Maybe you have a very, very large array, and this number could be in the hundreds or thousands. And of course, you need to plug the ADC into something, so there are interface requirements, both physical, what is the physical connector, that's going to mean you can plug this board into this board, and also what's the protocol, what does your ADC speak, how does it present data to your downstream processor, can your downstream processor read that data and interpret it in some kind of sane way. So, as you might imagine, there are lots and lots and lots and lots of ADCs available, both from CASPER and other folk. So just sort of an example of some of the ADCs you'll probably come across in talks that happen later this week about specific CASPER instruments. So one is this ADC 1X5000-8, usually just called the ADC 5G. It is a single channel 5 gigasample ADC, which means you feed in one RF signal on one of these coaxial cables via an SMA connector. You sample that signal 5 billion times a second. You stream the digital numbers out over this connector here. This connector is called a ZDoc connector. It's heavily used in CASPER boards. You'll see it all over our ADCs, all over our FPGA boards. It is now largely deprecated, so newer ADCs are moving away from that. But this is sort of canonical example of a CASPER ADC. Similarly, maybe you want more bandwidth, but you can get away with fewer bits. So then you pick a different ADC, in this case a faster one. So 10 gigasamples per second now. Now you can process 5 gigahertz of bandwidth simultaneously, but you only have 4 bits to play with. So this might be good if you're operating at high frequencies, where maybe you have less RFI, but you have more bandwidth you want to process. Again, largely it looks like every other ADC. You plug a coaxial cable in. It's got this funny connector. Hopefully your board you're going to plug into has the other end of that connector, and away you go. So lots of ADCs, do you want 8 bits or 12 bits or 14 bits or 4 bits? And do you want 10 gigasamples per second or 250 megasamples? You can pick. If you want lots and lots of signals but relatively small bandwidth, perhaps you want this 64 input ADC, which can digitize 64 analog streams, but only gives you 64 megasamples per second, so you can only process 32 megahertz of bandwidth, but over lots and lots of input, so really good for, say, prototyping a large array. And then at the other end of the spectrum, as I say, there's sort of very fast ADCs, but with a very small number of channels. All of these ADCs, because this is what we do in CASPER, use the same interface, and the idea being that they're all a bit plug and play, chop and change. With one processing board, you can just pick the ADC that matches and plug it in. So it's worth noting that while you'll see a lot of ZDoc connectors in CASPER, as I say, that connector is largely deprecated. In fact, I think our manufacturer, Digicom in Oakland, probably has the final stock in the world of those connectors. You will, in other ADCs, both those coming out of the collaboration and those available from commercial suppliers, a bunch of other connectors, FMC, FMC+, these come in large pin count versions, small pin count versions, mega ray, which is what you'll see on the SKARAB. All of these are just physical connectors that provide some connectivity from one board to another and provide different numbers of pins, different sort of speed limits about how many bits per second you can transfer through them reliably. And so you'll see a lot of these appearing on future ADCs in one form or another. So you have your ADC, it has some connector, in CASPER's case it's probably a ZDoc, then you need to go and process that data somehow. So broadly speaking, the general categories of processing in CASPER land are filtering, that's doing FFTs, which we've heard a lot about, cutting a big bandwidth up into lots of small bands. Correlation, multiplying pairs of antennas in an array, tends to be a very compute-limited processing step. Beamforming, adding signals together to basically create an analog of a single large antenna from multiple small antennas to create a sort of single beam. That tends to be a sort of I/O constrained or memory constrained task. But in any case, at least in CASPER, we're probably looking at using some variety of FPGA platform. So FPGAs, I think, in the next talk, Carrie will discuss extensively. But again, at the highest level, you can look at, when considering an FPGA board, two things. Kind of what are the specs of the actual FPGA on the board? So I should say at this point, an FPGA is a field programmable gate array, basically a reprogrammable logic chip. Very, very, very good at doing streaming operations, relatively simple signal processing, but on large quantities of data. Less good at doing very complicated things that you might, for example, usually do on a CPU. So you can ask of an FPGA, well, how many multipliers do you have? An FPGA itself is made up of lots and lots of discrete cores, and the goal of the FPGA designer is essentially to design a circuit that connects these cores together so as to do something useful, like implement a filter. So FPGAs have a bunch of multipliers. That might be hundreds, it might be thousands, depending what sort of chip you're looking at. They have a bunch of RAM on there, but not too much, looking at sort of hundreds of megabits, which is obviously much less than you'd find in a sort of personal computer. How much I/O does a chip have? Usually in CASPER we're talking about transceivers, which equate to Ethernet ports. This is basically saying how many very high-speed Ethernet links can a particular chip support. And also a slightly more hand-wavy concept of the number of logic cells, or the actual number of logic cells, is very easy to define, but how many you need for a given task is perhaps a little bit more tricky. But in any case, modern FPGAs, we're looking at sort of millions of logic cells. The logic cells are where you do very general purpose signal processing, so any of your sort of if statements, multiplexers, anything which can't be expressed as sort of an arithmetic operation or a memory block. So that's the chip, but of course the board has to do lots of other things to support the chip. So it might have, for example, some off-chip memory. That might augment the relatively small but very, very fast on-chip memory with potentially gigabytes of external storage. It almost certainly has some Ethernet ports of some variety. That's how we get data out of the board usually if we're building some sort of correlator or something which is connected through a switch, as Dan showed. And also sort of other auxiliary connectors. And this would include the ZDocs, the FMCs. This is where you plug in your ADCs and things like that. So more concretely, actual CASPER hardware. So as Jonathan said, not supported in this CASPER workshop tutorial session and now blissfully deprecated by Digicom. The Roach 2, released in 2010, is a Vertex 6 FPGA, so 38 megabits of memory, 36 transceivers, each one capable of 3 gigabits per second, 2,000 multipliers, some RAM, some other RAM that's not on the chip, which I didn't really describe very well there. 8 10 gigabit Ethernet ports, very impressive at its time, now not such a big deal. 2 ZDoc connectors, which is to say you can plug 2 ADCs into this thing, and an onboard CPU for sort of programming the board and talking to it. What does it actually look like? Well, this. So that's your FPGA, and on all of these boards you'll see the FPGA is always under the biggest heatsink. This is your CPU. These are the ZDoc connectors where potentially you would plug in ADCs. If you want to talk to the CPU, you can use just this 1 gig RJ45 port. So this chip essentially runs Linux. You can log into it like any old machine. It has some RAM here. And then it has these high-speed Ethernet ports. And in fact, on the Roach 2, the Ethernet ports are on these connectorized mezzanine cards, so you can choose what kind of physical interface you have. And there are a few that were sort of popular back in the day of Roach 2. So Roach 2 supports them both. Slightly newer than Roach 2. This one is supported in the tutorial. Snap One, still now about 3 years old. Kintex 7 FPGA, we've gone from the 6 series to the 7 series. Obviously, higher numbers equals better. So now, this is actually a relatively small FPGA. So Snap One targeted the kind of low-cost market. It was designed for the Hera telescope. So a few hundred multipliers, a little bit of memory, some transceivers. Note now that rather than the Roach 2 transceivers, of which there were a lot, but they only ran at 3 gigabits per second each, the Snap has 8 transceivers, but each one will run at 10 gigabits per second each. That means that each one of them can support a 10 gigabit Ethernet interface. And you'll see, unsurprisingly, as hardware gets newer, numbers get bigger, the amount of data I can transfer over a wire continues to grow. In classic CASPER fashion, we keep a ZDoc connector. That means if you've got some ADCs lying around, you can throw away your Roach 2, plug them into your Snap, and away you go. In Snap's case, perhaps quite unusually, but because it was designed with a custom experiment in mind, we have these 3 onboard ADCs. So this is a Snap sitting on top of an old Roach 2 lid, which is being used as a whiteboard, and I would suggest that's the best thing you can do with a Roach 2. So it's got these 12 analog inputs here. These are the ADC chips. These chips feed data via digital links to the FPGA. Again, the FPGA is the thing under the heatsink. Now you've got a slightly different connector for Ethernet. This is called an SFP connector. And no, not populated on this board, there's a slot there where you would put a ZDoc. And as well, you'll see sort of a bunch of other stuff which is present on all FPGA boards to a greater or lesser extent. There's a lot of power infrastructure here. So each one of these chips is a regulator responsible for outputting a particular voltage standard for some chip on the board. There are some LEDs here, which are nice because, you know, if an LED is not flashing, how do you know your FPGA is not doing anything? And sort of generic headers here, which perhaps we use to control some auxiliary stuff. Sometimes we plug a Raspberry Pi in there if we want to talk to a CPU. But yeah, so this is Snap One, and you'll see those in the tutorial room. Now getting into the bigger processing boards, released a couple of years ago, give or take, a Vertex 7, so the same series as FPGA as Snap, but much more powerful. Now we're looking at thousands of DSP slices, a bunch more memory, lots and lots of transceivers. SKARAB took a slightly different tack to Snap, where Snap put ADCs on the board. SKARAB went the other way and basically supported 4 mezzanine cards, so with one of these mega ray connectors, which is just a connector providing lots and lots of pins of interconnect. And onto those you can put your memory chips, which come on external cards, or your ADCs, or your Ethernet interconnects. So SKARAB is the board designed for Meerkat. It's many of them are chugging away in the Karoo, processing Meerkat signals. And this is a picture of that board. So again, you have an FPGA under a big cooler. You have some voltage regulation chips. You have these mezzanine card sites, which is where you plug in external peripherals. So in this case, they have one card populated, and in there goes some Ethernet. So now we're talking about 40 gigabit Ethernet, so a step up from the 10 gigs offered by Snap One. And the list goes on and on. Snap 2, now an even newer generation of FPGA, but ultimately looks quite similar. Big old FPGA, some mezzanine card slots. These are now FMCs, where you might plug in some ADCs, some Ethernet ports here. As Dan showed, I think, in his slides, you can plug in an expansion card on the back, which gives you even more Ethernet, and then you get essentially a sort of bajillion gigabits per second of I/O.
500.
Okay. You won't find Snap 2 in the tutorials. What you will find, which is something new from CASPER that came out of last year's workshop, conversation at last year's workshop, the Red Pitaya board. The Red Pitaya is based on a Xilinx system on chip, which means they've combined an FPGA and a CPU into a single package. Makes it very easy to talk to, very easy to treat like it's a computer, even though it has lots of FPGA resources. Relatively small by CASPER standards, but also very cheap. So whereas with the other boards, we're looking at sort of paying, round about $10,000, give or take, per board. This guy's about 300 euros, and so we have actually quite a few of those in the tutorial room. The idea being that this board, which includes, in fact, some onboard ADCs and some onboard digital to analog converters, which I haven't really talked about, is a good board for playing around with in the lab and sort of getting used to the tools that we use in CASPER. So exactly the same tools that program this board will let you program the more capable boards. And that is not a SKARAB, it is in fact a Red Pitaya. Nice small board, analog signals going here, gigabit Ethernet comes out of there, and again the FPGA, a little dinky one, under this, this heatsink. So there are lots and lots of FPGA boards. As you might imagine, they get better over time. The SKARAB did 40 gigabit Ethernet. Now you can very easily buy chips that do 100 gigabit Ethernet. Maybe they have big banks of memory built into the chips themselves. And so one thing that CASPER is looking at doing, and I think a lot of people in this room are exploring this, is using commercial cards. So this, for example, is a card from a HPC vendor, Alpha Data. And again, big old FPGA, lots and lots of Ethernet ports. These guys are all 100 gigabit capable, a bunch of power supplies, a bunch of little dinky connectors where you can add on more peripherals if you want. So those are the boards we kind of have to play with and the boards we're looking at using in the future of CASPER. Of course, you have to connect them all together, so for that we have transport. So one thing you'll see in CASPER is a lot of Ethernet. As Dan says, switches are free. Sometimes the cost is negative. It's not strictly true, but if you go on eBay, you'll find they are really very cheap. Typically, in modern CASPER systems, you'll see either 10 gigabit per second Ethernet, 40 gigabit per second Ethernet, or on the newer boards, 100 gigabit per second, usually plugged together into switches with 32 or 64 ports. One of the nifty things about the modern connectors used for Ethernet is that they can support either copper or fiber. So, for example, this is an SFP connector, which supports 10 gigabit per second. You'll see those on Roach 2 and on Snap. This is a 40 gigabit connector. You'll see those on SKARAB. But in fact, if you don't want your signals to only travel a few meters, if you maybe want to send them hundreds of meters or kilometers, then you can get fiber optic versions that plug into exactly the same ports. So this is in fact a 10 gig long range transceiver that's good for about 10 or 20 kilometers. And this is a 100 gigabit transceiver, in this case good for a few hundred meters. And so really, this form factor, this SFP, QSFP, QSF, the Q just standing for quad, which is this guy has 4 times as many wires connected, essentially, as this guy, so outputs 4 times the bandwidth. It melds very well into the sort of CASPER idea of modularity. So now, not only are our boards modular, but we can sort of pick and choose how much we want to spend on transceivers and therefore how far we want to send our data. And then you plug them into a switch, and switches all look the same. They all look like this. You plug a bunch of transceivers in the front. They talk to each other. Easy peasy. To close out, and I hope that when you go and do the tutorials, maybe this has helped a tiny, tiny amount in understanding what the actual hardware you're playing with is or does. Hardware gets better over time. Bigger numbers, generally better, except price. So sometimes we build cheaper things which aren't as good, and good luck keeping track, because there's 100 boards that get built every minute. And with that, I'm done.